Good afternoon, everyone. Thanks for being here. My name is Burak Berksoy. I'm the director for the RF engineering services within Netscout. And what my group does is we help mobile carriers make better design and planning decisions for their networks. And we do that by providing visibility into their network, even if it doesn't exist yet. And we provide accurate propagation models to create accurate predictions. We have limited time today, so our agenda is short but packed. We're first going to talk a little bit about what propagation models are, what they do, and why they're important. And then we're going to go into some of the lessons learned that we had during our data collection season in 2018. Particularly in the 5G domain. And at the end, we're going to do conclusions, and hopefully we'll have some time to do some Q&A at the end as well. So what are propagation models, and how are they being used? So before we even go into the what they are, I want to kind of start from the right side of the slide here. The predictive analyses. Why do wireless carriers do predictive analyses? Well, mobile carriers have incentives or certain initiatives to go to the next step, to augment their network, whether it's adding VoLTE, whether going into network densification, whether putting new 5G sites and 5G deployments. They have certain initiatives that they want to do, and they would like to figure out what sort of budget is required for that. So predictive analysis is a great example on how you can figure out the capital budgeting process for that. You can also provide marketing coverage analysis. Where will the marketing teams target certain audiences? And the design itself, these networks, deployments, you have to design, you have to determine where each site goes, what direction the azimuths look, and the tilts, electrical down tilts. All of that is being determined with predictive analysis before the network even exists. And even if the network exists, you can make design decision based on where should I add my next site? How can I get the most bang for the buck if I put my site over here in the street corner or on the rooftop or on a tower nearby? Those are all network decisions that you have to make, and those happen with predictive analysis. And typically, the tools that create these predictive analysis, they're called planning tools. And in the heart of these planning tools lies the propagation model. That is where the calculation happens. And the propagation model is basically a calculation tool to compute what the path loss looks like around a cell site. And the way that that's being done is by using parameters, model parameters. And what we do in Netscout is we go out and collect drive test data, so a ground truth data. These are measurements. And we utilize the geodata combined with these measurements, and we basically change these model parameters, and I put some knobs and dials in here as an analogy. They're not really knobs and dials, but in reality, they're parameters, and we change these parameters so that the predictive models accurately reflect the real-world measurements. And that's the exercise of model tuning. And at the end of the day, you hopefully have predictions that reflect what your network looks like in real life. So what's the impact of not having these models accurate? And so to say, if they either under-predict or over-predict your signal levels, what's the real impact of that into your network? Well, the consequences are, if you think that the signal is going to be less than what it is, if your design engineers will actually put the sites close to each other. And as a result of that, you will have an over-designed network. And the consequence of that is, of course, additional capital budgets that really doesn't really help your network. On the opposite side of things, you have the underplanned network. And that happens when the predictive models over-predict the signal levels. And as a result of that, your sites are further apart from each other. And when that happens, you end up with coverage holes. And that's also another desirable outcome because you lose customers within those coverage holes. If somebody is driving between two sites, there will be dropped calls and all sorts of negative consequences of having these type of under or over designed network. And just to, these are pretty significant impacts as well. Just when you look at it, if your network is, if your model is under predicting by only 3 dBs, and 3 dB is considered, a pretty small number in the modeling world, the impact of that is 41% additional spending on your capital budget. And if you imagine what a typical wireless carrier's capital budget is for, say, 5G deployment, that's a really significant number. So what did we do in 2018, and what are we going to talk about in terms of lessons learned? We have collected about 3,000 continuous wave measurements in millimeter wave bands, particularly in 28 gigahertz and 39 gigahertz. In addition to that, we've collected about 300 CW measurements in 3.5 gigahertz. In the US, that is called the CBRS band. And we created propagation models. We turned these drives into propagation models for the wireless carriers. And along the way, we had to overcome a number of challenges. And this presentation is about summarizing what some of the learnings are from those challenges that we had to overcome. And of course, we went across 38 states collecting this data and 55 major metropolitan areas in the US. So what's our lesson number 1? In this modeling exercise, we actually used 16 kits to collect the data. What does that mean? A kit is technically one transmitter and one receiver, but the transmitter has some amplifiers and a gain associated with the antenna. And the receiver is the same thing. You have the receiver antenna and you have the low nose amplifier. And one set of transmitter system and a receive system is, we call it a kit. So we use 16 different kits in our collection. That is 16 different 16 transmit antennas, 16 receive antennas, 16 LNAs, and power amplifiers. And these were identical in terms of the part numbers. They were not, we bought the same exact equipment 16 times, and we used that. So I call this the total system gain, basically the addition of all the gains associated with the antennas, power amplifiers, low load amplifiers, and all of that. And what we're looking at here, in the millimeter wave, these components, 16 of these identical components, have shown a significant variation across their gains, meaning 5 to 6 dB gain variation among each other. These are, again, identical parts. And when you look across the frequency, when you sweep across the frequency, you can also see that the gains, the aggregated gain of the system has been varying significantly, about 2 to 4 dBs across the band. So what's really the takeaway in here? If you're a carrier, if you're looking into deploying a network in millimeter wave frequency, that really means that you have to take into account these type of variations, perhaps in your margins when you're calculating the path loss margins. Also, you have to be careful about the equipment that goes into your system when you're deploying these components. You have to make sure you understand the variations that exist among each other. Next one is the cell edge. For this one, we use a measurement called D142, and I'll explain what that is. It's basically the distance from the transmitter at which you get 142 dBs of path loss. Why 142? That is a traditional number that is being used to demonstrate the cell edge, and that's a typical path loss budget for a system. That's why we use the 142. You can take that as the cell edge. In reality, your own networks may have more gain or more sensitive receivers. The path loss budget may vary from 142. but this is something that we have used for the purpose of this analysis. And when we're looking at the distances at which we consider this as the cell edge, in microcell environments in 28 gigahertz, we see the cell edge being about 350 meters. And in 39 gigahertz, that's slightly less, around 300 meters. And in the macrocell case, 550 meters in 28 gigahertz, and 450 meters in the 39 gigahertz. And you can see that as we go higher in height, as you go higher in height, the cell radius also increases. This is intuitive, up until a certain point where it probably doesn't help anymore. But in the range that we've tested, which was about from 5 meters to about 30 meters, getting the signal, the transmitter being higher has helped the propagation distances. Lesson number 3. Before we started these projects in 2018, one of the preconceptions was that if you don't have a line of sight, you may not have coverage. And early on in our process, and we kind of validated this over and over again, we have seen the majority of our data that we have collected, we've seen it to be non-line of sight. And it is true that you have significant losses if you have non-line of sight conditions, and you have significant diffraction losses in non-line of sight conditions in these frequencies. On the other hand, you have a lot of reflections from the buildings particularly. You get a number of reflections and multipath effects, and at the end of the day, you get a significant amount of coverage in non-line of sight conditions. So that's something to take into account. There's certainly an additional loss associated with the non-line of sight points. In average, we see that to be about 30 dBs, but you have to also consider the reflections into account. Lesson number 4, it's about geodata. The geodata input that goes into your system, they have to be high resolution because they actually help in the millimeter wave case. The wavelengths are so small, and as a result of that, what we call a Fresnel zone, that's a zone where the transmitter and the receiver have a meaningful amount of energy transfer. The Fresnel zone gets to be a very small number. If you're looking at a system that is a kilometer apart, in 700 megahertz in our traditional frequencies, the Fresnel zone radius, which represents the thickness of this level here, that used to be about 10 meters. Now, in millimeter wave cases, that is down to 1.6 meters. So if I have to do an analogy in the sub 6 gigahertz frequencies, it's kind of like having a spotlight that illuminates an area. In the case of a millimeter wave, it's more like a laser pointer going into a direction. And as a result of that, the uncertainties in the geodata have a large impact. Because before, if you had a plus or minus 1 meter accuracy, did not really mean much as far as blocking this Fresnel zone, which is 10 meters in thickness. But in millimeter wave cases, if that could entirely block the Fresnel zone for the millimeter wave case. So it's very significant. And also a recommendation when you're looking for geodata, look for finer resolution geodata. But nowadays, for 5G, most of the geodata that's available and what's recommended is actually in the form of a vector. So it comes in the three-dimensional shape of a building, or three-dimensional shape of a vegetation or tree. And one thing to kind of understand is what are the inputs that go into that? Is it the satellite images? Is it the LiDAR? Or what kind of accuracy they have? And these are all the conversations that you should have a discussion with the geodata vendor, and consider that for your millimeter wave design, because they have a pretty significant impact on your coverage. Lesson number 5. This is not necessarily a lesson that we learn in the 5G specifically, in the millimeter wave. This is something that we learned a long time ago and found a solution to it. And this is maybe this is a little bit to tickle your inner data scientist here about data. And it's about bias. So when you look at a CW measurement, you see the signal decaying as you go further away from the site, from the transmitter. What happens when you reach the noise floors is the receiver is not necessarily able to detect that signal from the noise. And you keep measuring the same signal level over and over again, even though you're going away from the site. And this type of bias exists if you're collecting data with the scanner or if you're collecting data with your phone. You have to be aware of what sort of signal you are getting, but also you have to be aware of what sort of signal you are not getting. You could be in an area where you are measuring a signal level, but your phone is not connected to the network, so it's not able to report that sort of signal level. That creates a bias as well. It's not just something that happens in CW drives. So the impact of that is, though, when you look at the line, if you do a straight line fit or straight least squares fit through your data, and this is a overly simplified version of a model, of course, modern day models are much more complicated with 30 plus parameters, and I'm oversimplifying this down to 2 parameters. The impact of that is overestimation of the cell edge. All these measurements that you have in this region particularly, because of this saturation, they tend to bias the data if you're doing a straight line fit through it. And at Netscout, we have created a patented technique to overcome this effect. We call this the dynamic range limitation, and we call the technique we use dynamic range compensation, and we overcome the impact of that. So let's talk about some of the conclusions that you can take away. Propagation models have a significant impact on your network design decisions, and at Netscout we try to provide you with the tools to make better decisions on your network design and planning, and propagation modeling is one of them. And we provide the accurate propagation modeling through our process. In terms of the millimeter wave equipment, be aware of these variations that we talked about. There are variations between identical components. They vary from their specifications. How much they vary is something that you should be keeping an eye on if you're doing a deployment on your own network. We know it's not a new thing. It's not a surprise that the cell edges are shorter. We kind of discussed 300 meters, 350 meters, up to 550 meters in certain settings. But it is not that you have to have line of sight. You can have coverage in non-line of sight conditions. And finer resolution geodata is important to have, but be aware of the inputs that go in there. Vector layers, particularly, they are generated technically, vector layers have infinite resolution. You have to be careful and understanding of what the inputs are that goes into those vector layers. And finally, the propagation models itself, you have to understand the propagation models as well. What data goes into it, what sort of biases may exist in there, how we actually mitigate that type of effect is something that you should be looking out for in your networks and be careful about. Any questions? Sure. I'm going to provide a microphone.
Why didn't you use a modulated signal?
Sure. So that's a very good question, and it's a common question that comes across. The question was, why didn't we use a modulated signal? In CW modeling, typically we use a narrowband signal, and it's not modulated, first of all, because the limitation of the bandwidth. We want to use as small of a bandwidth as possible in our tests. And the second part of it is, particularly in millimeter wave frequencies, also the question comes up as, why don't you look at angle of arrival and different type of parameters, the delay spread and other characteristics of signals. And we don't look into them because we can't really use them for modeling purposes. The modeling is a simplified version. I mean, I should say, the aim of modeling is to get an understanding of how the signal propagates in a simplistic manner. We don't want to overcomplicate the models because they would take forever to compute. As a result, they're simplified versions of what really happens in real world in physics. So some of the components of angle of arrival or delay spread, things like that, don't really get computed. They don't translate into the models, and that is the reason why we don't really collect that type of data. Understood? Okay.
Hi, it was a very nice talk. You said in millimeter wave band, between two identical components, you get to see 5 to 6 dB of variation. Can you say what's the reason? Any idea? Why do you see that?
Well, I don't know the exact reason. That's more of a question perhaps for the equipment manufacturers. But what we find is this is not an effect that we were seeing in lower frequencies. We used to have a very consistent gains across the components that we've seen, and we've done over 25,000 measurements in the lower frequencies in 700 through 2100 and such. This wasn't an effect that we were seeing, and the equipment manufacturer that we used to get our components is considered one of the high-end equipment manufacturers. So we believe this is an effect that is related with the frequencies, and every component of it is more, of course, sensitive. If you think about, in the lower frequencies, we work using cables. In millimeter wave, we are using waveguides, and you can have easily dirt can get into waveguide, and it can impact its gain. And so every component is much more sensitive in the millimeter wave frequencies. And that's the reason why we believe that we're seeing that type of variation. Yeah.
Hi, which propagation model you use for this study, and any recommendation for the model that fits with 5G?
Yeah, a very good question. As Netscout, we use the propagation model choice of our customers. In these particular projects, we use the Aster propagation model with ATOL. And we, of course, use the millimeter wave. They have a new millimeter wave release of the Aster model, and we use that one. As far as the recommendations go, I don't believe I have used all of them to make a proper recommendation, but we used the Aster model, and we've gotten very good results with it. So, yeah. Any other questions? All right.
Hi. You stated that the Fresnel radius decrease in the millimeter wave case, that will result in greater geo inaccuracy. So you have to go with what, finer geo points?
Yeah, let me clarify that.
Yeah, I got kind of a little
yeah,
confused.
so if I go back to the slide, the first part of that statement is correct. As you go higher in frequency, the Fresnel zone radius is inversely proportional to that. So the Fresnel zone radius decreases. The impact of the geodata inaccuracies, if you think about, let's say I have a 2 meter, plus or minus 2 meter inaccuracy or uncertainty in my geodata height, okay? So if you imagine this Fresnel zone versus this Fresnel zone, if I have a plus or minus 2 meters, it's going to only block about maybe 10% of this Fresnel zone. And if I have a plus or minus 2 meters inaccuracy in my in the millimeter wave case, it may block the entire 100% of that Fresnel zone. So it's not because the Fresnel zone, it doesn't have any impact of the geodata, but the geodata uncertainties have a larger impact on the predictions because the Fresnel zone is smaller. Yeah. Okay.
Just another question on the narrowband predictions and measurements. How do you do the conversion to a wideband signal? Because obviously the 5G signal could be 100 megahertz wide.
Yeah.
So how are you doing that conversion, particularly given it's OFDM?
Yeah, so, I mean, in the case of path loss, the path loss itself does not vary by the bandwidth. It does get impacted by it. It may have variations across the bandwidth, but the path loss itself is not dependent on the bandwidth itself. So that usually gets taken into account in the link budgets. There could be certain margins that are incorporated because the measurements are done in relatively narrow band, and then they're used for a much wider bandwidth. And in the case of 5G, you're right. I mean, the bandwidths can be 600 megahertz. They're very large bandwidths that we're looking at. Okay. Any other questions? Can we get the mic here?
For the issue at the beginning that you're talking about, the variation from equipment from one instrument to the other, is it an issue because it's a time variant concern, or is it? Can you just calibrate it and resolve the issue?
It's not time variant. We're making these measurements in a lab environment, so there's no real variations in the environment. There are no cars passing by or so. Those measurements are done in the lab environment. And it's just the behavior of the, so there are two components to my statement there. One is the variation between components. It's a pretty significant, but they're consistent. So we measure that out, and then we calibrate, of course, into our models. Each one of our kits, each one of our measurement devices have their own gains and losses associated with that. So we do make those measurements. But in terms of the frequency, if you think about, for our purposes, we can calibrate that into our modeling process. But when the carriers have to apply those into wider bandwidth, of course, there will be a lot of variation across the band for it. And again, it's one of those cases that need to be incorporated as a margin in the link budget. Okay. I think we have time for one more question, maybe. No questions? All right. In that case, thank you very much, and a great show.